In the rapidly advancing field of robotics, dual-arm coordination and precise object manipulation are crucial for building advanced autonomous systems. These capabilities are essential in areas like healthcare, manufacturing, logistics, and even domestic assistance, where robots need to handle complex tasks with both arms working together seamlessly. However, one of the biggest challenges in developing these systems is the lack of diverse, high-quality training data and reliable evaluation benchmarks that truly align with real-world conditions. This is where the RoboTwin framework comes in, as described in the research paper titled, RoboTwin, Dual-Arm Robot Benchmark with Generative Digital Twins. Authored by a team of researchers from institutions including HKU, Agilix Robotics, Shanghai AI Laboratory, and others, RoboTwin is an innovative approach that leverages cutting-edge AI technologies to generate realistic data and testing environments for dual-arm robots. At its core, RoboTwin uses 3D generative foundation models and large language models to create what's called generative digital twins. These digital twins are virtual replicas of real-world objects and scenarios, allowing researchers to simulate and test robotic behaviors without the need for extensive physical setups. The process starts with just a single 2D RGB image. From this image, the framework employs advanced 3D generative models to reconstruct detailed, interactive 3D models of objects, complete with realistic textures and physics. This means you can take a simple photo of, say, a kitchen item, and turn it into a fully manipulable digital version that behaves like the real thing. What makes RoboTwin particularly powerful is its ability to produce a wide variety of expert datasets. Traditional methods for collecting training data, like human teleoperation, involve people remotely controlling robots to demonstrate tasks. While this works, it's expensive, time-consuming, and doesn't scale well to cover all possible scenarios. In contrast, RoboTwin automates this process. It generates diverse demonstrations by varying object placements, environmental conditions, and task complexities, all within a simulated environment that's closely aligned with the real world. To achieve this, RoboTwin incorporates a spatial relation-aware code generation framework. This system combines object annotations, detailed descriptions of the object's shapes, positions, and properties, with large language models, like those similar to GPT. The language models help break down complex tasks into smaller, manageable steps. For example, if the task is to pick up and assemble two parts with both robot arms, the framework first analyzes the spatial constraints, such as how close the objects are or their orientations. Then, it generates precise code for robotic movements, ensuring that the arms coordinate effectively without collisions. This framework doesn't stop at simulation. RoboTwin provides a comprehensive benchmark that includes both simulated data and real-world data collection. This allows for standardized evaluation of dual-arm robotic tasks, bridging the gap between virtual training and actual performance. In their experiments, the researchers used an open-source platform called the COBOT Magic Robot to validate their approach. They pre-trained robotic policies on data generated by RoboTwin and then fine-tuned them with just a few real-world samples. The results were impressive. Policies trained this way improved success rates by over 70% for single-arm tasks and over 40% for dual-arm tasks, compared to models trained only on real-world data. One of the key innovations here is addressing the limitations of existing benchmarks. Many current systems focus on single-arm tasks or simple bimanual setups, which don't fully capture the intricate coordination needed for integrated dual-arm systems. Previous works, like MimicGen or RoboCaca, generate simulated data but are often limited to fixed scenarios and struggle with variations. RoboTwin overcomes this by being highly scalable and adaptable, using generative models to handle novel situations without requiring task-specific redesigns. The paper highlights how this generative digital twin approach enhances efficiency in data collection. For instance, Figure 1 in the paper illustrates the overall pipeline, starting with 3D generation from foundation models, moving to aligned code generation, and then collecting both simulation and real-world data to create diverse datasets. This not only saves time and resources but also ensures that the training data is more representative of real-world variability, leading to more robust robotic systems. In practice, this means that researchers and engineers can now develop and test dual-arm robots more effectively. For example, in a manufacturing setting, a robot could learn to handle delicate assembly tasks by training on varied digital twins of components, reducing the risk of errors in the actual production line. The use of large language models adds another layer of intelligence, as they can interpret natural language descriptions of tasks and translate them into executable robot code, making the system more intuitive and user-friendly. Overall, RoboTwin represents a significant step forward in robotic benchmarking, demonstrating how combining 3D generative models with language models can create a more efficient, scalable, and real-world aligned pipeline for dual-arm manipulation. By generating diverse expert demonstrations and providing a standardized evaluation platform, it paves the way for faster advancements in autonomous robotics, ultimately helping to deploy these systems in more complex and dynamic environments.